Hello, welcome to this session. In the previous session, we looked at inverter based ring oscillator and where we control the frequency of the oscillator by controlling the current through the ring oscillator. So, let us just look at it. Inverter based ring oscillator is something which we studied, and what we told that if we want to control the frequency of the ring oscillator, we can control the frequency of the ring oscillator by controlling the current or by changing the load. So, here if you remember what we did, we controlled the current somehow x. So, we did this, and by the way, we control both the top and bottom. So, here we applied a current mirror, and the current mirror was finally controlling the current. So, this was our V control. An important point here is the following, that in this ring oscillator which you see, right, as you control V control, you are changing the current through the ring oscillator, right. So, I will mark this voltage, so the overall voltage as VDD, okay, and the voltage which is supplying the voltage which is at the source of the PMOS in the inverter is VDD VCO, VDD of the voltage controlled oscillator. Okay, and similarly, you have this lower voltage. This voltage is not ground; it is actually ground for the VCO. Yes, in the previous session, I called this as local VDD and local ground. Now, the thing is that because this VDD is for the oscillator, so we can call this as VDD VCO and ground VCO. Important part here is that if you take this oscillator stand alone, this particular node, I call this node is VDD VCO and this node is ground VCO. Okay. So, to make it more clear, if you say that I am having a voltage source whose voltage value is VDD VCO, and I am having another voltage source whose voltage value is ground VCO, right. Then whether you have the oscillator as you see on the right hand side or you have the oscillator on the left hand side, both the oscillators will operate at the same output frequency. The output frequency is going to be same. So, I call this as I VCO. So, the only difference here is that in one case you are controlling V control, because of the change in the V control you change the current here, right. So, I call this change in the current delta I here, right, delta I VCO. So, when you change the delta when you change the current in the oscillator as delta I VCO and your frequency of the oscillator is some value, right, then you will automatically get the voltage VDD VCO and ground VCO. You are not directly fixing the value of this voltage VDD VCO or ground VCO, you are fixing these two voltages indirectly. What you are doing is you are controlling the current through the oscillator, and because you control the current you will get the voltage automatically. In the other case, I am whatever voltage somehow it develops here at the top and bottom VDD and ground VCO, here I give these voltages VDD VCO and ground VCO, then you will automatically get the current I VCO, whatever the current I VCO which you have here, and both the oscillators will operate at the same frequency. Okay. So, it means that if I can control for if you just simplify it further, and if you say that I have this ring oscillator connected like this, one of the node can be ground or it can be some other potential. So, I am connecting it to ground for easy circuit diagram here. So, if I take this oscillator and just a copy of this, okay, you have this oscillator, right. In one case, what I am doing is I am forcing the current I VCO such that it develops a voltage, let us say VDD VCO 1. In the other case, I apply a voltage source VDD VCO, okay, and here you have a current I VCO 1. Okay. So, if VDD VCO is equal to VDD VCO 1, then you will have I VCO equal to I VCO 1, and if the frequency of the oscillator is going to be same, let us call this as VCO 2 and this as 1 and this is 2. I think that will make much easier. Okay. And your F out 2, which is the output frequency for the second oscillator, is same as F out 1. Also, if I make sure that I VCO 1 happens to be equal to I VCO 2, then in that case it is quite it will be quite clear that VDD VCO 1 is equal to VDD VCO 2. Okay. You may think that this is an easy this is how it should be, right. The thing is, if we understand this, then what we can do is we can have a voltage controlled oscillator or a current controlled oscillator. Both of these can be used. So, what I can do is, if I want to have a current controlled oscillator, then I can just use a current source with VDD here and apply a control voltage which controls the current, and I keep this as an oscillator. So, what you are doing here is effectively, though you are changing the control voltage, but actually in response to your control voltage you are changing the current through the oscillator. You are not fixing the voltage VDD VCO directly, okay, that is what you are not doing. Whereas, if you want to have an ideal voltage controlled oscillator, what you can do is you can use a regulator to fix the output voltage. Okay. So, I will give this as V control, and with respect to this V control, then this V control feeds to your oscillator. Okay. So, this is there, these are all grounded. Okay. So, this is VDD VCO. The amplifier, you can have the amplifier connected to VDD. This is one way. So, here if you look at it, your VDD VCO is directly controlled using V control. If the amplifier has enough gain, then your VDD VCO will always be equal to V control. So, you control the output voltage or the voltage which is connected as a supply to the inverter, and that is how you control the output frequency. In the first case, you control the voltage to the voltage of the gate for the current source, which is PMOS, and thereby you control the current. Okay. And in response to the current, your frequency will change, right. So, normally you can say that this is a current controlled oscillator, you are controlling the current, Okay. CCO is short form for that, and the bottom one is voltage controlled oscillator. Because you control the voltage, for the or the supply for the inverter directly. Okay. So, one thing is also there that whether it is a current control oscillator or a voltage control oscillator, the ring oscillator is going to oscillate at the same frequency. Either you give the same current in both the cases, or you somehow you maintain the same voltages in both the cases. So, there is no difference with that. It is just that what you control and what is the cause and what is the effect. Your V control is the cause, right. You change the effect is IV. So, you directly change the current. Because you change the current, the frequency changes. Okay. Now, so what we have seen so far is we have seen inverter based oscillator, and in order to control the frequency of the inverter, we actually ended up controlling the supply voltage or the current of the oscillator. Okay. Now, one interesting thing here is that let me just tell you, there are two things which we do not understand so far from our basic stuff. One, this oscillator, when we control the supply of the oscillator, so we control the supply VDD VCO to change the output frequency, whether we change the current or we change the supply. At the end, we are changing the supply voltage of the oscillator to change the output frequency. So, this out signal, if your supply of the inverter is VDD VCO, which is going to be always less than equal to the VDD in a given process. If that is the case, then the out signal is not going to swing more than VDD VCO. So, the swing at the output signal is going to be limited by VDD VCO. Now, where does our logic stand? That initially we were using a small swing oscillator, we shifted to full swing oscillator because that is more useful, right. The swing does not depend. Now, we are saying that in order to control the frequency, you change the supply voltage. So, the swing argument has gone to toss. Okay. So, what we have to do something that can restore the full swing without compromising on our frequency tuning. Okay. So, what we need to do is we need a block where the output of the oscillator. So, output of the oscillator comes here, and finally, when we get let me call this as a clock out, we should have full swing signals rail to rail 0 and VDD. We want such kind of block to help us. Okay. So, this out signal is this, right. So, that, and we do not want to change the frequency, we just want the whatever signal you have here, this signal you have previously, the signal as shown here, that gets restored to 0 to VDD, and nothing else do we want to change. So, this block should act as a buffer for the clock, where the clock frequency is retained, right, as the only thing is the swing is amplified to full scale. Okay. So, one way to do is the following. So, what we have seen here is that an inverter is used in the oscillator. So, we are going to use a similar inverter here, whose supply is not VDD VCO, but VDD itself. Okay. So, this is not a VDD. So, if I give any signal here at the input, whether that is whether that signal is 0 and VDD VCO or VDD, the output of this particular inverter is going to be full swing, because if you have a simple inverter, then yes, what you will see is something like this, okay, and this kind of signal you will have. Right now don't go over the crossing points, but this is what you will see at the output. So, this seems that okay, if I want to buffer the clock, I can just connect an inverter, and then I can get the full swing. But actually what happens is that because you have an inverter, right, this particular inverter, you will have a threshold voltage for NMOS and PMOS in the inverter. So, with respect to midpoint here, you may see this whole as t by 2, whatever the time period you have, and this also as t by 2. But when you give this signal to an inverter directly, what is going to happen is that you will not get the same duty cycle. So, the inverter which is designed with 0 to VDD here, that inverter will have crossing point like this. Those crossing points will be at VDD by 2. Those crossing points will not be at VDD VCO by 2. So, your duty cycle will get distorted. Okay. So, what is going to what we should do here is the following, that somehow we have to restore the duty cycle and buffer the clock. So, for that particular purpose, so you can say a clock buffer is something which we need to design, okay, and we need to retain the duty cycle. So, let us say you are getting out from your oscillator, and you are going to AC couple that output of the oscillator to an inverter which is self biased, okay, and if it is self biased inverter and this is grounded, you are going to connect this to the supply VDD, and then it follows regular inverters connected to VDD. Okay. So, it is connected here, same. So, if you look at the clock here, this particular clock will have full swing, and it will be actually having 50% duty cycle if you have symmetric waveform here. So, this capacitor is AC coupling cap, which is CAC. When you connect the inverter back to back like this, well, there will be capacitance at this node also. Let me call that as Cp. Okay. So, when you have an inverter which is connected back to back, what you are doing is the following. So, Cp is just a model of the cap which I have. What I am doing, I will just first draw the inverter here the way we are having in our circuit, and this is connected back to back, and all the other inverters are same, there you are not connecting back to back. Okay. Now, this is your out and this is your signal. So, you can model this. So, now the thing is that Cp is the capacitor which will come on its own because of these MOSFETs, PMOS and NMOS. You need to decide on the value of CAC such that your output frequency is buffered. One thing, that if you bias the inverter, self bias inverter which you have, then inverter input to output characteristics we have seen before, they are something like this. So, normally you can design an inverter where you have input and output values as VDD by 2. This can be done. Okay. So, you have that way, choose the PMOS and NMOS sizes accordingly, right. So, this is a nominal operating point, you get this capacitor. So, when you have any frequency coming here, right, what that signal is going to see? That signal is going to see a loading because of the PMOS and NMOS current sources here and CP both. So, what you need to do is you need to choose your CAC value in such a way that whatever signal you get here, actually the same signal comes here. The question is whether same signal will come here or not. So, let me call this as Vx. So, in order to find out, I will first assume that okay, I can model this inverter which is self biased using its linear model. So, I will have Cp, Cac, and this is nothing but because drain and gate are connected. So, you are going to get GMP and GMN. So, I will just write this as GMP plus GMN times Vx. They act as a load, okay, and here it is V out signal coming from your oscillator. So, Vx by V out, this is a simple circuit. You have GMP plus GMN Vx, right. So, effectively this will act like an impedance of 1 over GMP plus GMN. So, what we are having is 1 over GMP plus GMN, right. This in parallel with 1 over SCP whole divided by 1 over SCAC plus 1 over GMP plus GMN plus parallel 1 over SCP. So, that is what you have, the transfer function. So, to calculate that value, 1 over GMP plus GMN in parallel with the 1 over SCP is going to be equal to, so the parallel impedance is going to be equal to 1 over GMP plus GMN times 1 over SCP. There is nothing difficult here, GMN plus 1 over SCP, right. So, what you get is GMN plus GMP plus SCP, right. So, that is what you have here. So, this Vx by V out which we are looking at, this is 1 over GMP plus GMN plus SCP whole divided by 1 plus SCAC plus GMP plus GMN plus SCP. Okay. So, this is equal to, you are having SCAC divided by SCAC plus SCP plus GMN plus GMP, which now this is something which you need to understand. So, we have SCAC divided by GMN plus GMP, okay, 1 plus SCAC plus CP whole divided by GMN plus GMP. Okay. So, this transfer function is actually a high pass transfer function, and for this high pass transfer function, what you see, there is a pole, and pole is at GMN plus GMP divided by CAC plus CP. So, versus frequency, if I plot, or versus omega for that matter, if I plot this, it is like a high pass transfer function, and then it will become flat. Okay. What is the value at which it will become flat? Well, the value is going to be, so we are trying to evaluate at a very high frequency that you can easily evaluate, and that is equal to this value is CAC divided by CAC plus CB. It just acts like a capacitive divider, and this value is less than 1. Okay. So, that is what you will have, and the pole frequency happens to be at GMN plus GMP divided by CAC plus CP. So, when you are choosing this capacitor CAC, you need to understand this transfer function. First, we want this gain to be close to 1. So, what we want is whatever frequency is coming at the input here, the same frequency should, the same magnitude should come here, that is ideally required. If you do not do that, if you choose your CAC in such a way, so let us say one curve is like this, another curve where your CAC is actually is smaller, another curve may be like this. So, this curve, let me just pick a value, is 0.95, this happens to be 0.7. So, your output swing will get reduced, okay, that will happen. The other thing is the frequency which is present at V out, your cutoff frequency should be smaller than the frequency of the frequency at the input of the buffer. Okay. So, that this frequency, whatever your F oscillator or omega oscillator here, this should be greater than GMN plus GMP by CAC plus CP. Second, if you want that the amplitude should not degrade, then you should make CAC large, okay, large such that the degradation in the amplitude is lesser. That is how you need to choose it. So, typically you will not choose a lower value of CAC, because if you choose a lower value of CAC, your amplitude will reduce. Then you can say, okay, what is the problem even if amplitude reduces? So, what you will see is, if I, for example, if I am having this as a 1.8 volt supply, my swing which I am getting at the input happens to be like this, where you have 0 and this is for example 1.2, right. So, what you are going to get here is whatever the common operating point, which is 0.9. So, at 0.9 I will get plus minus 0.6. So, this is going to be 1.5 and 0.3. That is how the swing will appear at Vx, and this swing will then be amplified by another inverter based on how much, what inverter you are using. So, this may get amplified to 1.8 or maybe 1.75. So, it will take a couple of stages. If your swing is low at Vx, it will take couple of inverter stages to amplify that particular signal to full swing. Okay. Now, whether it is good or bad, well, when it is amplifying, it is also adding noise to the system, that is a white noise, but that is what will happen. So, ideally you would like to get whatever swing is available here, you would like to get the same swing. If it is amplitude of 0.6, you would like 0.6 to come here, you may not be able to do it, you may get maybe 0.55, 57 or something, but do not choose the capacitor value CAC such that the amplitude reduces, that will be more problematic. Okay. So, that is what we do. Then the question, you can ask a question, well, if a large CAC is something which we require, then why do I go and calculate it? I will just use a large capacitor, much larger than CP. Well, if you do that, let us say you choose a much larger capacitor, the problem is not the amplitude, the problem will be your actual frequency itself. And what is that? It is your CAC with CP is in parallel with your impedance, your 1 over GMP plus GMN. This acts as a load for the oscillator. Okay. So, it acts as a load for the oscillator, and ZL value you know is 1 by SCAC plus 1 over GMP plus GMN plus SCP, right. So, you have an impedance here which is going to be, so let us just look at GMP plus GMN plus SCP plus CAC divided by SCAC into GMP plus GMN plus SCP. Okay. So, you get the impedance, which is you get impedance loading on the oscillator. Now, well, this is just a series of one capacitor and another RC, right. So, here if you think about it, that I choose my 1 plus CAC much larger than, or CAC capacitor happens to be much larger, I do not care about it, just 10 picofarad or something I may use, then this impedance, this is an approximation. So, this impedance is going to be negligible, right. If this impedance becomes negligible, this impedance dominates. In this combination, it is like you can say the capacitors which are added up in series, right. So, if CAC is quite large and this impedance is going to be much lower, it is close to 0, just an example, and this impedance dominate. So, effectively you can say that this impedance loads your oscillator here at the output node. If you load your output node of the oscillator by any impedance, right, this is GM plus CP, depending on among GM and GMP plus GMN and CP which dominates, you can get okay which is the dominating factor, or overall you are having this impedance. It is going to load your oscillator, and if it loads your oscillator, it is going to alter the output frequency. Any loading like RC loading is going to reduce your frequency of oscillation. So, it is not always advisable not to worry about the CAC. You can use at any given time, you can use a large CAC and it will work. Well, it works for the amplitude, but it actually lowers the frequency of the oscillation also. So, while choosing this CAC, please optimize this such that the frequency of the oscillation is not that much compromised and you get good amount of swing at the input of the inverter's chain for your buffer. Okay. So, to convert the oscillator, just to give you a complete picture, you can actually do this, right. So, I just need to connect it like this here, and this is going to be connected to a buffer chain. Okay, this is connected here. All these are connected to full VDD. Okay. This CAC. You do not connect any CP. CP capacitor will come on its own. Okay. That is how you convert limited swing of the inverter to full swing for the full swing clock at the output. Okay. Thank you.